participating. So just a quick overview to the organizing committee, just to provide you with a general view of the people who will interact with you during this week, and a brief overview of the program of the school for this week. You can follow both theoretical lessons on the fundamentals of robotics and application in healthcare, but in parallel we will be also involved in practical activities related to workshops and team working. So we are going to start with the first day of the school, that is basically focused on theoretical activities and lessons. But as you can see here from the program, in the next days, you will be more involved in practical activities and also in a team, in a competition for going to the last day with the competition discussion of your activities and also the final award. So this is the program for today, and I will leave the floor to Professor Hirata, who will be the chair of the morning session and who will introduce our first talk today. So I invite Professor Hirata to start chairing the session with the first talk.
Okay, thank you very much, Loredana. So, hello everyone. We'd like to start the first session. But first of all, thank you very much for joining this seasonal school. So I'm one of the organizer, and I'm very happy to welcome you to this seasonal school. So, so at first, I'd like to introduce the first speaker of this seasonal school, Professor Cecilia Laschi. So she's a professor at the National University of Singapore, and her research is in the field of soft robotics. So she's a member of the IEEE of the Engineering in Medical Medicine and Biology Society and of the Robotics and Automation Society. So where she serves as elected ad hoc member and co-chairs of the TC on soft robotics. So she founded and served as general chair for the first IEEE RAS International Conference on Soft Robotics, RoboSoft, in 2018. So this means that she is a very, very expert in this region, research area. So today, today's talk is soft robotics from bioinspiration to biomedical applications. So, okay, I would like to welcome the Cecilia. Okay, could you share your screen?
Yes, sure. Thank you very much for your kind introduction. I'm going to share my screen. I hope you can see it fine.
Yeah, it's fine.
So thanks a lot again for your introduction, for inviting me. I'm happy to be the first speaker, so I will try to introduce you to the field, mostly to the field of soft robotics, and you will go into the details of the seasonal school topics in the next days. So before starting, let me share something about myself. As Professor Hirata said, I'm a professor at CNUS in Singapore. I arrived here quite recently this year from Italy. So I've been a professor at the Biorobotics Institute of Scuola Superiore Sant'Anna in Pisa since last year. And this is where I did my soft robotics research recently in this beautiful lab in Livorno. So my research, it was already said, but it started with actually neuro-robotics. So I first work on, let's say, on the brains of robots, and then I moved towards their body with soft robotics with my octopus-inspired research. So let's now learn about something about yourself. So if you can kindly connect to the address that you see here, this paulev.com/my name. even with your smartphone, you can then participate to some polls that I organized during the presentation so that we can interact a bit. I give you another minute, but then I will go. So you see it's quite easy, paulev.com/my name and surname as one word. Okay, so I hope you could easily connect, and I go to the first poll. So where are you from? So it's the first day of the school, and it's nice that we know each other. Italy is being crowded. South America, US, Africa, Japan, Mexico, India, Japan again. So a bit more European, I see. Some Americans. Turkey here. More coming. So we have Africa, I guess, South Africa. I don't see why. UK, France. Okay, so a good class. Okay, thank you very much. I mean, I see some interesting variety of country here, and you're what? PhD students mostly, maybe? Yeah, I mean, definitely the majority for now. Still the majority, some master students, so that's interesting. Still the majority are PhD students, which makes sense. And master students. Okay, very good. Very good. I got to the next question, but last one, don't worry. So a bit about your field. So because my presentation contains several topics, you can even click more than one, because robotics is quite general. So biomedical engineers, that's good. And some of you have some familiarity with soft robotics, it seems. Very good. Okay, so this is more or less what I expected, because you see my unconscious bias. I already ordered the fields according to your actual fields. Okay, thanks a lot. So let's go into the topic of my presentation at last. So you see this title, Soft Robotics from Bioinspiration to Biomedical Application, but this is actually what, I mean, soft robotics is very much part of the broader field of biorobotics. And biorobotics, for me, it's really this balance between bioinspiration, so where we apply engineering tools to study biological systems, and biomedical applications. So we use engineering for developing devices for biomedical applications. So let's get started with the bioinspiration first. So what's bioinspiration? This is a quite vague word. And I use this definition by Vincent. So it's using principles from biology. Okay, this is the bio part of the word, to stimulate research in non-biological science and technology. So it's not very detailed. It's still a bit broad, but I mean, we like this. Actually, you find many words in literature that respond to the same definition. So you find biomimetics, you find bionics also with this meaning. You find the bioinformed design, which recently is very much used, and so on. But for the scope of this lecture, let's keep all of them as synonymous. Now, to you again. Do you have some examples of bioinspiration that come to your mind from your, I mean, everyday life, not from your research? Something that you meet every day in your everyday life. Interesting. Sisters are bioinspired because don't be shy. You use plane before COVID. Yeah, plane is questionable because, of course, flying is bioinspired. I mean, Velcro is very good one. Plants is biological. It's not. Okay, had civilization of birds, but an object that is bioinspired. Octopus is biological. Pipes, I don't understand. Not very clear ideas. So actually, there are many objects in our daily life that bullet train is a good answer. Velcro is also an excellent answer. Okay, that's a general principle. And that's these are more principles that we can take for bioinspiration, but something that you meet every day, because there are more objects that you think in. And Velcro again, okay, we know that's and that's my actually next slide. So I will show you some examples and you will realize that there are several in our daily life actually. And I put just a couple of them, but so this one is the discovery of an engineer, the Mistral, you know, going around hiking with his dog. What he found is that some plant parts, these birds, could attach to the fur of his dog and also his clothes, as you see, but they could be detached. That's the interesting part of this story. So he observed under a microscope and he found that there are these small hooks, and the hooks are perfect for the fur of the animal. And actually nature did so because of the possibility to transport the birds. And this is how he invented Velcro. And some of you answer correctly to this. So Velcro is one of the most popular bio-inspired objects in our everyday life. This is another example that was also mentioned by someone. So the bullet train. Okay, it's a long video. I skip a part of it. I mean, the train is fantastic. The fastest one, it was introduced in Japan, with two big problems. One was the tunnel boom. So a very big noise when entering the tunnels because of the change of pressure. And what was done was to redesign the shape. This is the engineer, Eiji Nagatsu. And he observed that kingfishers enter the water without any splash because of the shape of their beak. And that's how he redesigned the shape of the front of the train. The second problem was the noise of the pantograph. And again, he observed that the owls fly very silently instead. the pantograph is this part of the train that you know it's necessary for getting power. And he observed that owls fly very silently, and this is due to the fact that the structure of their feeders create micro vortexes instead of big vortices. And that's why a noise is reduced so much. And this is the way the pantographs were also modified to reduce this noise. I have another example here. I'm sure you know that, but I'm not sure you know that it is bioinspired. So this is again an engineer, and what he is observing is a bone. And you see he's observing the internal structure. You know that bones are quite empty inside. So they are organized with these trabeculas, but the let's say that the arrangement of the trabeculas is not just random. So of course, having an empty space is helpful to reduce the weight, the overall weight of the bone, but we still want it to be very robust. And trabeculas are actually oriented along the main lines of force acting on the bone. So it is very strong, but light, as light as possible. Do you see what this man is designing? Yes, to Reifa. Because his problem was to build the tallest building at the time with iron, which is quite heavy, so it would have collapsed under its own weight. But, I mean, inspired by bones, he oriented this artificial trabeculas along the main lines of force, given by gravity, basically, and he could build a tall and robust building is still there. Of course, there are also good examples of bioinspiration in robotics. This is the Gecko, which is very much studied in robotics because it has a very interesting adhesion, dry adhesion, and that allows it to basically climb on any surface. And if you observe it on the microscope, you see that there is a hierarchy of structures that actually generate this beautiful mechanism for dry adhesion that was copied in this StickyBot at Stanford University several years ago by Professor Karkowski, but it's still a very impressive example of biomimetics. So this field is growing not only in robotics, not only in engineering, actually taking inspiration from biology, working with biologists is increasing the number of scientific discoveries and technological advances in many fields. So it's a successful interdisciplinary approach. In robotics as well, these are my own data. If you look at the bio-inspired robots or biometric robots, they are also growing in terms of scientific results, in terms of publications. But this nice article a few years ago on Nature analyzed this and said two things. First of all, we're just scratching the surface of biological inspiration because we always refer to basically the same species. And another important point is that to have successful results here, we have to team up with biologists. And this is really important because if we do bioinspiration as engineers only, we tend to do some mistakes. And one mistake that we tend to do is that we select our model. This is a human being, but can be any animal, plant, and we just take the individual. And we tend to forget that what we are observing is actually the result of evolution. And goals of evolution is based on natural selection, and the goals of natural selection are quite different from engineering goals. They are basically survival, so finding food, and reproduction. And what we observe is not optimal design because it's something that changes when the environment requires adaptation, requires change. So beautiful in terms of adaptation, but if you look at it in terms of optimal design, it is not, because it is a revision of something that was already existing. So that's why we shouldn't just copy. Simply copying is just wrong for many reasons. Sometimes it is not even feasible. But what we should do is to extract key principles that can be helpful in our engineering problem. So I think that this nice combination of biology and engineering can work if we learn how to do good implementation of principles from biology. This is what gives the good science that we have seen. To do that means teaming up with biologists and having a feedback that improves even more this beneficial loop. So what's this good implementation of principles then? My opinion, this is of course my own view on Bioinspired robotics in a correct way is of course taking the principles, as I said, as a first step. And as roboticists, we can already build something that help us understand the principle better and verify the principle better. But it is only when the principle becomes something formalized mathematically. So only when it becomes a mathematical model. So only when we can abstract the principle into a mathematical model that it becomes engineering. So here we can build prototypes, a prototype again, a robot prototype that help us verify the model. And only at this point with the mathematical model, we can design our robot. And that will be our bioinspired robot, which doesn't mean having the same shape or the same appearance of the model we started from. This is a sort of misunderstanding that we sometimes find in robotics literature. So if we put this process here inside here, this can become our good implementation that can be interesting for biologists, even in the first phase of verifying principles with mockup. For sure, it is interesting for biologists in the second phase when we model mathematically the principles that we observe, and we have this beautiful closed loop. And at the end, we have also our good engineering, our good robot for some intended applications. Let me give you a couple of examples. So I already mentioned the Gecko-inspired dry adhesion. As you see, there is an observation here of the hierarchy of the compliance structures in the Gecko fit, and an implementation of them with some engineering tools, what's possible technologically, and you see that we still have a hierarchy of compliance structure in the robot, in the StickyBot. So my question, is StickyBot a good example of biomimetics, bioinspiration if you want, based on what I explained? Yes, no, and why? More answers are coming. All answers are for yes. Someone there is a no. Okay, I'm not sure of the total number, so let's close here. Okay, so the good answer is yes. The correct answer is yes. Okay. Why? Following what I said, we have to identify a principle in the biological system, try to implement the principle. So the correct answer is yes, because the robot adhesion is based on the same principle of the Gecko adhesion, so the hierarchy of compliance structures. The fact that the robot shape is similar to the Gecko body shape is not so important to be bio-inspired biomimetics. Let's see this one now. This is from BBC News, you see. Okay, muted. And BBC say, okay, this is a Starfish-inspired soft robot. It is soft, it can crawl, it can move. You're probably very familiar, this robot is very famous. It was done at Harvard a few years ago. Very famous in soft robotics. Is that a good example of biomimetics, bioinspiration? Again, yes, no, and why? Someone is there, some no's are appearing here. Still the majority is for yes. Okay, I think most of you have answered now. So, sorry, this is not a good example because there are no principles taken from a starfish. It's just vaguely, very vaguely the shape. But the principle is completely different because this is actuated pneumatically, so nothing to do with how a starfish can crawl. That's it. But I mean, it was a trick from me because I go back one slide if it's not catastrophic. Actually, the authors never said that it is Bioinspired. You see, the paper is a multi-gate soft robot, but it's BBC, it's the journalist that said, okay, it's a starfish inspired because probably they saw something similar in terms of shapes, but this is not a bio-inspired robot, don't want to be. Okay, let's go on with this journey from bio-inspiration to biomedical application. So we said first step is bio-inspired principles. In my own research, I mean, I found a gold mine of principles in the octopus because it is completely different from a robot. So it is completely squeezable. It can elongate its arms. It can bend the arm in all directions at any point of the arm length. What is interesting is that it's not soft. I mean, it's not correct to say it's soft. It is soft, but it can stiffen the arm when it is necessary for generating forces. So there are so many principles that we can take. But let's say that for me, the main lessons that we can take from nature is this one. For robotics, I mean. Because we tend to think that our robots are complex, but actually any biological system is way more complex than any robot that we build. So animals and plants as well, they are incredibly complex systems in terms of degrees of freedom, if you want to use robotics terms and sensors. And the environment is also very complex compared to, I mean, structured robotics environment. So what we should learn is how such complex systems can work so smoothly so effectively and efficiently in a complex environment. So we don't want to simplify our robots or our environments as we tend to do in robotics, but we should understand the principles for complex system working efficiently in complex environments. Okay, this concept is very much related to a concept that you're probably familiar with, embodied intelligence. Are you familiar with that? Never heard about it? Good. Very good. So most of you knows it, but part of you never heard about it. Very few have a clear idea, but that's a good point because in the end, I mean, embodied intelligence is very much a concept, a bunch of ideas more than a real discipline. So it's that's very consistent. Let's see a bit about it. So embodied intelligence is basically this new view of intelligence that say that, okay, the way we move our behavior and any biological system is not just the brain thinking and the nervous system transmitting signals, but it's also given by the body itself. So I mean, our movements, our sensory motor behavior emerges from the interaction of the body with the environment. And of course, in relation to the task we want to do. And then, okay, in robotics, that can be very helpful because we can simplify many tasks if we take this into account, embodied intelligence. Okay, but as roboticists, we want something more than this. So where is embodied intelligence in a robot? If you consider a typical scheme where you have a sensory system taking information data, sensory data from the environment, then you have some form of controller that uses this sensory data and generates motor commands for the mechanical systems that acts on the environment. Embodied intelligence is the mechanical feedback from the environment directly into the mechanical system. So you skip the whole loop. It's just a small, very small closed loop here in the mechanical part of the robot, but you need to be able to grasp it and to allow for receiving this mechanical feedback. So the body has to be compliant, and this is exactly what brought us to soft robotics. Okay, said that. How can we define soft robotics? You can choose more than one answers. Nobody dares? I don't see answers appearing. Is that a... Oh, okay, sorry. So it was just a delay. Now I see them. Very good. Very interesting. I see a few answers for the moment, but I don't know if it's my delay or... Let's speed up a bit because... very good. Okay, so I will probably go on, but I see that for the moment, the winner is robots composed of materials with moduli, elastic moduli, in the range of that of soft biological materials. Second place is robots that undergo large deformations for their inherent or structural compliance. Okay, good. Let's go on. Actually, it was a bit of a trick because you find all of them, almost all of them, in literature, in papers, in reviews on soft robotics. I go a bit faster here because they are exactly the definitions that I gave in the poll. This is the one about the material elastic module. This is the one I like better, which was also in the poll, and it was in the second place. So for me, I mean, coming from the idea of implementing embodied intelligence and I mean, having a compliant body for interacting with the environment, this one is the most comprehensive because it has two parts. So of course, the material that is soft, like in this completely soft robot, but you can even use materials that per se are not compliant, like plastic, like in this case, but arranged in structures that are extremely modifiable. So both things, low elastic modulus or high elastic modulus, but with this deformable geometry. Okay, so where is the embodied intelligence in the model that I want you to take, that I said it's a gold mine of principles? This is one of the most studied movements in the octopus. And you see that, of course, it's very efficient in water because the arm is bent, is almost folded into parts, and the bending point propagates towards the end of the arm. And of course, there are many, many muscles involved here. So as a roboticist, you would be crazy thinking of controlling something like that, infinite number of degrees of freedom. And it's quite, quite complex to propagate it. But if you take only the physical part of the story, so this silicon cone has only same mechanical properties, same density, similar shape, you see that when you move it in the water, it tends to bend and to fold into parts and to propagate the wave. So this is done by the water only, basically, and this acceleration at the base. So of course, the octopus is controlling the movement, but the movement is helped a lot by water. And actually, if you look at the neurophysiology of this movement, you find that the brain only set 3 parameters. So body matters very rudely, and control is simplified by the interaction with water. Let me skip this one because I'm getting a bit, I want to convince you that body matters and the environment matters, but let's go to the secrets of the octopus, which is the muscular hydrostat. It's a special muscular structure with longitudinal and transverse muscles, so that when they contract the transverse, they elongate the arm because it's a volume constant structure. And the opposite, when they contract the longitudinal muscles, the arm shortens and the diameter increases. Also, bending can be obtained because these longitudinal muscles are along 4 main, they are in 4 main bundles. So when just one is contracted, there is a bending on that side. There are also oblique muscles that are for torsion, but I skip this. What is more interesting is that co-contractions generate the stiffening that I was mentioning. We did some measurements, but let me also go through them quite fast because they're not so relevant. What is relevant is that, okay, we got the principle, we love the muscular hydrostat, but then we need technologies to try to do a similar thing in robotics. So these principles give us incredible incredible challenges on the research side.
Can I ask one question? Sorry, I interrupted.
Yes, sure.
I couldn't understand how you actuated the material that in the previous slide you explained.
It was not actuated. That's the point.
Okay.
So it was really only the physical body and the interaction with water.
Okay, sorry. That's why
that's,
I missed that.
very good point. Very good point.
Okay.
Yeah.
Thank you.
Okay, so yeah, after studying the muscle hydrostat, we tried to actuate something like that, and what we wanted to test was the coupling between the transverse and the longitudinal contraction in the animal that generate this stiffening between the base of the arm and the bending point. We also tested silicon, you see in the left, and we found that some of the commercial silicon similar to the octopus tissue, which is the black line, which is good and bad. I mean, we were so happy because silicon is so easy to use, and still today, many groups in the world use silicon in soft robotics. On the other side, that's too, how can I say, too good, because we don't look for other materials, while I think there is a lot of space for research on the materials also. We tested some other smart materials like electroactive polymers that we arranged in this stacked structure, and we wanted to build a muscle hydrostat out of that, but it's a bit complex to handle all these actuators. And we went finally for SMA springs. So each spring can simulate a bit a muscle contraction, especially because of this braided structure around it. So you see how a transverse contraction can elongate the arm, and you see longitudinal springs in the video, and this is another video with let's say our final arm prototype, where the SMA springs are arranged transversely. And in this prototype, longitudinally, we have some cables that can do this nice bendings. And we can see how the activation of all cables can shorten the arm, while activation of all the transverse springs can elongate the arm. And what is used today in soft robotics around the world are this kind of technologies to some extent. So electroactive polymers, shape memory alloys. But what is really very much used in, let me, sorry, I'm trying to remove the audio, sorry. What is really popular in soft robotics today is fluidic actuation, especially pneumatic actuation. So I'm sure you're familiar with many systems that are based on chambers. That's very convenient because you can set the shape of the chamber in any, I mean, creative way, and guided the formation with some tricks like stiffer materials on one side. So this is definitely very popular, and as you see, it's not really bio-inspired. There are also some interesting principles, again, not really bio-inspired, like twist and coiled or the jamming mechanism. In control as well, we need some new ideas because at least in soft robotics, in soft robot control, we have more transformation. It's not just the motors that set the joint space, and the joint space is related to the task space. Here we have actuators that just produce a deformation. Deformation changes the configuration space of the arm, and finally you have a new position of the end effector. But it's a bit more complex. still, I mean, if you can find the relations between, I mean, that describe this transformation, you can apply just the same kind of approach. And there are some methods that are used in soft robotics for modeling these deformations. So the most popular are the constant curvature or piecewise constant curvature, but there are also some other methods like geometrically exact method like the Coursera approach, or even FEM is used somehow inside control loops. And this is just to give you an idea that there are controllers based on such models. All the boxes that you see with the inverse kinematics based on those models are used in control loops. Let me skip this. So are they good? Are they not? They are, to some extent, to the extent that the models are good. In literature, you find that they mostly rely on CC approximation, the constant curvature. And if you want to use more complex models, computational cost increases. So that's why model-free approaches based on learning are also tested in soft robotics. Not only in soft robots, you know, neuro-controllers are used on any robot, but here it can be nice to, of course, you can use any kind of learning. And what is nice is to replace some of those boxes with some learning boxes. This is what we did with our first octopus arm. So a neural network that does exactly the job of a controller, creating the transformations between the end effector position, the tip of our arm, and the, let's say, the actuator space. The actuators here are our cables. So the cable tensions is what we want to set. And we could develop this, let's say, Jacobian-based control compared with the neural network on the same arm. And what we obtain is that, of course, the Jacobian method is more accurate in simulation. When we tested it in in the real prototype, we obtained quite different results. And so we want you to see it better. I see an invitation to go in the speaker room, but must be an error.
Yes, sorry, you can start for the disturbing you. We just had to open it to allow the next speaker to try his presentation.
Okay.
Please just everybody stay here and continue to enjoy the show. Thank you.
I couldn't hear well. Anyway, I'll try to speed up a bit. What we found as expected is that the Jacobian method increases its error when the error of the model increases. While for the neural...
excuse me, I interrupted.
Yes.
Can I ask you one question?
Sure.
For this method, basically, you say Jacobian, so you're, let's say, giving some pretensions in the certain range and checking the endpoint and point velocity. It works
actually,
like this, or
no, we had what I didn't say is that we had a model of the arm deformation. So and that was a geometrically exact model. It was based on the crossroad road. So we could have the relation between the tension at cables and the deformation of the arm and the final position of the tip. This is what is inverted.
Okay, and also in the previous case you explained about model-based control. Do you, let's say, creating some point cloud in the space by giving some inputs, and then you're basically optimizing, or let's say linearizing a function, and then you are applying say inverse kinematic?
Actually, no. What we did, of course, it's a quite basic neural network. So there was a training phase, and the training phase was giving tensions at cables and getting the final position of the tip. And those two data became the training set for training the network. Okay.
And also you are checking repeatability, of course, I think.
Yeah, of course. Yeah. And of course, the network has some inaccuracy.
Okay.
But you see, this inaccuracy is constant with respect to, I mean, it's the same for any arm on any prototype, even if it's let's say wrong in fabrication.
Okay, thank you.
You're welcome. I think I have to skip a little bit of this, but just to say, neural network is what we use in for controlling our soft robots, and it's not just because we don't want to build models, but because I think they can better encode embodied intelligence, morphological computation. And this is especially visible in dynamic tasks, like in this dynamic controller. We find self-stabilizing trajectories here. So in this video, let me skip a part of it. This is just a circular trajectory. It's a dynamic controller, and when the arm is perturbated, so it is pulled away from the trajectory, it tends to go back to it. And this is done with no feedback. It's just the mechanical structure. I'm sorry, I don't see the point where it is perturbated. Okay, it's here. You see, and that's just based on the mechanics. So it's quite qualitative and just, I mean, hint, but it goes into the direction of embodied intelligence. Okay, so all these technologies for what? What I think is the great contribution is soft robotics technologies, that we can think of abilities for our robot that were not possible before, more biomorphic in some cases. This is just a view of what is possible today with the soft robots that was not possible before. So you can see robots that are built with materials that can self-heal. We have seen robots that shorten and elongate, robots that grow by adding material that work underwater that was not possible before. There are, I mean, impressive results of, like this robot with a vascular system, the jamming principle used for adaptable grasping, and robots that can be completely squashed and they continue on to work. And all these abilities, again, for what? Where do we want to arrive with soft robotics are the application. So what we want finally in robotics is to enable more applications for robots. And there are many growing for soft robotics and definitely biomedical. Biomedical field is one of them. Especially, I mean, there are, especially when there is an interaction with the patient, surgery, rehabilitation, assistance, and then personal care, of course. Do you have any idea of a robot that is a soft robot and that is used in the biomedical application? You can just write here. Exosuit is a good answer. Flexible needle. Yes. Laparoscope, of course. Yeah, the soft exoskeleton. Prosthetics, maybe some hands. Laparoscope was colonoscope. Yes. Soft tissues is not a robot. Splint are usually not soft. Hand rehabilitation, yes, I saw something. Flexible endoscope. Okay, very good. I'm sorry, I'm running late, so I need to stop your answers here. But you mentioned most of the cases that I'm doing here. I try to organize the application of soft robots along how much they have to be mimetic. Of course, artificial organs must be very mimetic, while assistive robots don't need to, or biocompatible. Of course, artificial organs, they go inside the human body, so they need to be biocompatible. Body simulators need to be very mimetic, but not biocompatible. A few examples from my group. Is a soft endoscope that can actually change its stiffness, similarly to the octopus are. This is instead an arm for assistance to elderly people. Sorry, I'm having quite a delay in my own laptop, so I show you just the final video. So the idea here is to have antagonistic actuators, so pneumatic and cables, so we can control the stiffness of this arm. It is intended to be sort of robotic shower. And this is the implementation, the installation into a rehabilitation center in Rome. And just a view of how it works. Can detect the person and help showering. An interesting field, unexpected for robotics, is building realistic simulators of body parts. And this is our work on the larynx, which is a quite complex organ. And its working principle is based on the stiffness of materials. So that's why it is a very interesting case for soft robotics, and we built a prototype where we have a vibration which is similar to which is inside the physiological range of vibrations of vocal folds. And this is a project by Matteo Cianchetti that you will see in the next days during the school. It's the objective is fully soft artificial organs. So let me rush to the conclusion. This is a quite active field. So the number of publications really grew very rapidly in the last years, and also the quality of the publication grew a lot, the quality of journals where they appear. And for this rapid growth, soft robotics is now at a crossroad. This is a viewpoint paper that was published recently on Science Robotics. So the authors argue that the next period can be either this continuing growth, maybe at a lower pace, or a decrease of interest in the subject with minimal impact. And they say it depends on us. So it depends on the kind of research we do and the levels of contribution of our research. So the level 0 was okay in the growing phase of the field because the advancement is basically showing a new system, new technology, new mechanism that do the same thing. But we should either go towards level 1, which is a contribution, but still a bit limited because it's limited to the soft robotics field. While if you can give contributions that are in general to the progress of robotics or other fields, that would be the right impact to have this field really growing. Okay, so my summary, we have seen how from Bioinspired principle, we came up with soft robotics, but the Bioinspired principle are also very, very important for giving us challenges on fundamental research, which brings to new technologies in robotics, soft robotics technologies, and in turn, they enable lifelike robot abilities that enable more robot applications. And as I just said, hopefully to respond to global needs, not only in the field of soft robotics. Just an announcement, there is a TC in the Robotics and Automation Society on soft robotics, which is also very active. It won the best TC award a couple of years ago, and actually related to the TC is the conference in soft robotics that started in 2018. The next one is next spring in Edinburgh, and there are student competitions here, so this is a call for you. I'm finished. Before leaving, if you just want to share one word what soft robotics means for you in your own activity, if it is part of your activity. Just one word. Beautiful. Compliance. A thesis, someone is doing a thesis on soft robotics. Very good. So safety and compliance are the most very good. So my next slide is just thanks. So we can leave this one and this one going, and I stop here. Thanks. I just say thanks to all of you for listening.
Okay, thank you very much, Cecilia. So your talk is very, very impressive. So thank you very much. So although the time is limited, so we can accept one or two questions. So if you have a question, please raise your hand by using the Zoom function. So we can accept one or two. Okay. Radik Lama, sorry, Lamohan.
Yeah. So, ma'am, one question that I have is, you said that in order to model complex systems in soft robotics, data-driven techniques are used, overcome the problem of computational intensiveness. So, doesn't using data-driven technique also is a computationally intensive exercise, right? So, how it overcomes the earlier method?
I'm sorry, I'm not sure I got your question correctly. So okay. You say data-driven methods are, are usable, are affordable in soft robotics? Is that?
Data-driven techniques are also computationally intensive. Then yes. How it is advantageous over the conventional models?
No, actually, I mean that when I say neural networks, I mean they are data intensive during the training phase. So, for example, in our neuro-controllers, we need a long training phase. So, yes, the number of data positions that the robot has to reach is very high, but that's just during the learning phase. When they work, when you're controlling your robot, actually the computational time is very fast, very short compared to other controllers. I'm not sure I got your question, but maybe we should move on and you can write me if you wanna continue.
Thank you, ma'am.
Thanks.
Okay, thank you very much. So are there any questions? I can accept one more question. Okay, Miranda.
Hi there. I just want to say, first of all, thank you so much for such an interesting presentation, Cecilia. And I had a small question out of curiosity, because you mentioned about trying to keep it as realistic to the initial biological principle as possible. And one example that you gave was this phantom larynx, this artificial larynx that you said had to vibrate within the vibrational frequencies that are typical for a larynx. So if you pushed a biologically inspired robot to perform outside of the biologically inspired limitations of that organism, can you no longer refer to it as bioinspired?
I'm sorry, you said if you push the robots to be
so if it's performing outside of the performance frequencies, for example, the larynx, that it would typically perform, but it proved to be useful in a particular application, should it still be referred to as bio-inspired or not?
Yeah, for me, yes, because for me it is bio-inspired because we try to understand the principles by which we talk, and the principle is that we have in each vocal cord the 3 layers of different tissues with different compliance, and that's why the superficial one can vibrate. So this is the kind of principle that we, let's say, copied. I mean, we took and we implemented in our artificial vocal cord. So we also kept the shape, and the size, of course, is a bit larger, but it's especially the principle for obtaining vibration that makes them bio-inspired, biomimetic for me.
Okay, thank you for explaining that, and thank you again for the presentation. Really enjoyed it.
Thank you. I'm showing my last slide, so there is my email address, because I'm sorry I was a bit long and time is probably over, but you can write me.
Okay, thank you very much, Cecilia. Also, this is thank you very much again for your great talk. So,
thank you.
Okay.
Thank you.
Okay, we'd like to move on to the next session. So next is a workshop. So I'd like to introduce